Good morning, everybody. There we go. Okay. How you all doing today? Let's see. I was asking if you had a good weekend, but most likely it feels just like every other day in the week, right? Let's see. Where are we at? Get chat back. Come on. There we go. Awesome. All right. Is everybody ready to get going? Word of the day. Oh, Robertson, you're really holding my nose to the grindstone. I have to keep on top of this, right? Word of the day today. Ungulate. There you go. It came up in categories yesterday, and they didn't believe me that it was a word. There you go. It's the only thing I could think of that began with U. Anyway, so that's a bit of a tangent. All right, yeah, get off of that. Okay, so today we have actually starting on the, in my opinion at least, some of the really, really interesting stuff. So
my name is Stefan Patron with UPS. I'm your UPS representative for UPS Count Eaton Airflex Cleveland. I wanted to reach out to you and introduce myself. I wanted to be a little bit more familiar with your business and shipping processes. Also want to know if there's been any changes with your operations due to the coronavirus that's been going on. So if you can please just give me a call or send me an email, a good time to reach out to
Kara,
you.
I think your audio's on. If you could turn it off.
550-4184. My extension is 114-2171. My email is spatron@ups.com. Here's a call.
Kara, turn off your audio, please. Thanks. As interesting as it is to hear your phone messages, I don't think you probably want everybody else listening to them. Okay, so you know, no, don't worry about it. Where was I? Get off. So Mars is really, really interesting, right? Obviously, as an environment and as a potential site for life, and the fact that it's so close obviously lends it an awful lot more importance, right? Because we can actually send stuff there. It's a terrestrial planet. You can literally walk around on it. But in terms of astrobiology, I think actually the two kind of really interesting places are the moons of Jupiter and the moons of Saturn, right? In particular ones of those, because being gas giants, they obviously have a huge number of moons. I can't remember the exact number for Jupiter. I think it's 79, something nuts like that. It's you can see. Can you all see the PowerPoint? I think I've shared it with you. Presume so. No one's saying no yet. Anyway, these are just some of the orbits of those moons, right? So there's a huge amount of moons. Anyway, so really the reason for those places being so exciting is because they're host to moons, large differentiated moons, which almost certainly have liquid water on them, right? So the key candidate in the Jovian system is Europa, right? Which actually, let's make that a little bit bigger. There you go. Second Galilean moon from Jupiter, right? In the Saturnian system, it's Enceladus, right? It's a very analogous moon, right? So we're not going to talk really about Europa today. That's going to be, I think we're going to talk about that on Friday, maybe Wednesday, see how things go. But anyway, those moons are, I think it's pretty much 100% guaranteed to have some kind of liquid water under their surfaces, not on them, right? Because they're too far away to have liquid water on their surface, but they almost certainly do underneath their icy crust. Anyway, so we're going to get, essentially what I want to do today is kind of refresh your memory about the Galilean moons, tidal flexing, right? So we've talked a lot about different sources of heat in terms of planetary or moon environments, right? And obviously, if you look at this here, this is kind of one of those slightly irritating pictures, which kind of does what I want, but not quite. This is the order of the planets in the solar system, right? So we have our inner terrestrial planets here, and we've got our outer giants, and Neptune is kind of over there to the right, basically. The reason why it's a little annoying is because even though these planets are to scale, they're not to scale to, well, they are to scale to the sun, but the distance is not to scale. Right, so basically, I looked it up just before this, so I could give you a handy number. The diameter of the sun is 100th of its distance from Earth, essentially. So this should be, if it was to scale, it would be it'd be over there by quite a long way. Obviously bigger, right? Because it's considerably more massive than even Jupiter, but it's going to be a long way that away. But anyway, essentially what we have is if you can see my cursor kind of scooching up and down, the asteroid belt is about here, and this is where the frost line is. So Jupiter is about 5 times further from the sun than we are. So it receives considerably less insolation. What is that? The square root of 5, whatever that is. I think it's square root. Yeah. Anyway, so the heat in those moons does not come from the sun. Doesn't come from basically differentiation and formation, right? Because they're not massive enough. It comes from, at least in the case of Jupiter, I'll have to look into Enceladus for Saturn. I'm not 100% sure about that. But for Jupiter, it all comes from tidal flexing. So really, there's the big point of today's lecture is to talk about, just to go into tidal flexing in a little bit more detail and to recap that for you, and then to look into essentially the Galilean moons and then Io in particular, because Io is a funky ass place, right? And so I'm always kind of excited talking about Io because Europa is obviously where all the business is at in terms of astrobiology, but in terms of extreme environments, Io has it beat. Okay, so those are the two things really that I want to do today. Really reinforce the whole concept of tidal flexing and orbital resonances which cause it, and a little bit more detail on tidal flexing too, just to kind of, as I understand it better, I can hopefully teach it better. That's the aim. And then an overview of the Galilean moons, because they are all very different as a result of where they're at, relative to Jupiter and each other, and then a little bit on Io, because it's fun. All right, have some coffee. I don't believe I've heard Paul's dulcet tones today. That's such a cute picture of you and your cat, Kiara. I have to say, oh, there Paul is.
How's it going?
He's just being quiet. There you
Oh,
go.
I am. Golly gee, let me tell you.
You're what?
I'm just being quiet.
Oh, okay. Oh, don't. It's much more fun when people talk to me. Otherwise, it's like I'm just talking to a screen.
Just absorbing like a sponge.
Oh, good. Yeah. Well, don't, try and become a little like a hard surface and bounce that summer back at me if you can.
Hi, Dr. Crook.
Hello. Who's that?
Hi. I just had a quick question. I'm sorry it took me so long to sign in.
Oh, is that Pedro?
Yes.
Oh, hey, Pedro.
Hi. Can you put all of the Zoom link stuff in course content?
They are there.
Oh, really? Okay. Well, I mean, like the login links.
Oh, yeah, those are in the announcements. Ship it. Come on. How do I get this out?
Oh, okay, let me look for that. And
yeah, I'm trying to get rid of the Zoom stuff.
it took me like 25 minutes to find it and to find my email.
Come on. Sorry, I've got to. God damn it. All right, I'm just going to have to. Well, yeah, so it's in the course content.
Okay, I'll look for it again. I didn't.
Hang on, not course content. It's in the announcements, have all of the details. Course content has a couple of guides on how to use Zoom. And all of the previous Zoom sessions are, at least for now, in the course content in the solar system and extraterrestrial environments folder. I think that's what it's called. I would show you, but I can't because
No,
Zoom
it's fine. I'll look. I'll look again. I'll look again. Thank you so much.
Yeah, no worries. Okay, let's get back to this. So, just to give you another cool image of relative size, I don't know what that is down there. I'll have to go have a look at where that image came from again. But obviously you can see a big contrast between Jupiter with its red spot, giant storm, and there's a big polar storm up here, and Earth, right? So it is absolutely, literally massive, right? And we don't actually know what the center of Jupiter looks like because its atmosphere is so thick and so high and violent as well that essentially nothing that goes into it survives for very long. Same with Saturn too. So actually the standard operating procedure for probes that go to these places so they don't crash onto moons that might support life is to fire them into the planet, right? And they break up. The Cassini probe lasted for a little while before it was torn to pieces. But anyway, these giant storms that kind of rotate constantly around the planet. Super, super cool. Anyway, oh, and they also have like crazy lightning too, and we'll get into what causes that in a second. Okay, so the Galilean moons there's 4 of them, obviously discovered by Galileo Galilei. And actually the Galilean moons, they're originally called the Medici moons or Medician moons because those were the rich guys that paid his salary basically from Venice, I believe. Anyway, those Io and Europa, which he observed rotating around Jupiter, were actually the foundation of the heliocentric model. So those were the observations that led him to propose that the sun did not, pardon me, rotate around the Earth as was thought up until that point. Anyway, there are 4 of them. They orbit pretty close, right? So these are the 4 Galilean moons, and here these yellow orbits. So they're actually pretty close to Jupiter if you think about the relative scale of the size of the planet and the orbital radius compared with, say, Earth and the Moon. That also has pretty big consequences for Io, which is actually within the magnetosphere of Jupiter. So it'd be like the Moon being within the magnetic field of the Earth, which it's not. It's much further out than that. So they vary in size a bit. Ganymede and Callisto are quite a lot larger than the other two. And they also vary a lot in their properties, and we'll get to that in a wee bit. So just to give you an actual scale comparison, right? This is the giant red spot, which you've probably all heard of. So it's a perpetual storm that's raging in Jupiter. I think I'd have to double check. It's not too far off the size of the Earth, let's put it that way. It's really, 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 really big. And these are kind of the relative scale of the Galilean moons to Jupiter. Now, I just wonder if I can get this thing back. Can I get this back? Yeah, let's stick it over there. Oh no, it's raining. Bugger it. I was going to go for a bike ride after this. Anyway. So what I want to show you, the reason why I put it in presenter mode, is it's an animation, but this is actually what it looked like around June last year. You can actually see the shadows of Ganymede and Io. So Ganymede is the third one out, Io is the first one in terms of distance. And you can actually see, obviously, Jupiter's rotating, but you can also see the relative scale of these moons with Jupiter, right? So they are pretty small relative to the planet. What's also really neat is, I don't know if you noticed, but Io started way behind Ganymede, and it basically, there you go, and it basically catches up, and that's because Io completes 4 orbits of Jupiter in the time it takes Ganymede to do 1. Let's get that back over here. Okay. Seen this already? Just give you that idea. Okay, so this is pretty important. So I want to spend some time on it and make sure that you all understand it, because it's absolutely central to really everything that we're talking about in terms of characteristics of these moons and their potential for life. So essentially what we have with the inner 3, let's go back into this. Can you all see the animation on the left? Hopefully
Yeah.
Yeah, it's pretty cool, huh?
Love a good GIF.
Yeah, it's amazing what you can find on the internet. Anyway, what this is essentially showing is that it doesn't show everything, because that would be a little bit too complicated, but it's showing that Io, Europa, and Ganymede at periodic times in their orbit align, right? So they do it with the flashing colors. There's one coming around here, like that purple. And once every 7 days, they're all in the same position relative to each other. So obviously, I think, what is that? That's probably, Io does it, orbits in 1.5 days or something like that. On Earth days, at least. So what this means, and so I was talking about the relative changes of the gravity that Io experiences, and we'll talk about Io because the effects are most pronounced for Io. And that was a little bit of an oversimplification, right, for purposes of getting a concept across. What's actually happening is that Ganymede and Europa pull Io out of a circular orbit. So what you see here is you have these on the left-hand side, you've got these circular orbits, right? That's actually not quite the case. So when, let's say, just then, right, when Europa spins round and it is aligned with Io, Europa is going to tug Io a little bit further out away from Jupiter. So Io's orbit is not perfectly circular. It's what is it, elliptical? Yeah, elliptical, right? So it's more like, and it's a little exaggerated on the diagram on the right, but it's not a perfect circle. And because it's not a perfect circle, the gravitational pull of Jupiter on Io varies during its orbit. Essentially, the closer in Io is to Jupiter, the more gravity experiences versus further out it is. So essentially what, if you imagine kind of Jupiter's here and Io's going round, essentially whenever Europa kind of goes round at the same time, Io gets pulled a little bit further out. Then Io passes because it's going half the speed essentially of Io. It's not quite the right word, but you kind of get the idea. And then it goes back in a little bit, right? So essentially Io at every point, it's not doing like a corrugated orbit or anything, but its orbit is not smooth, right? So every time it gets pulled out, it essentially springs back to round a little bit. And then when that tug goes past, Ganymede or Europa or whatever, it gets pulled further in back to Jupiter and gets squished a little bit. Then Europa goes past again, tugs it back outwards, goes round. And so essentially, Io is constantly doing this. If we've got Jupiter over here to my left, your right, it's whenever Io or Ganymede go round, it gets pulled out a little bit, goes round, and then gets pulled back in by Jupiter, and it goes a little bit squished. Does anybody know how high the tides are? How, like, the greatest difference in water levels on Earth based on the moon? Just out of curiosity.
No idea.
It's about
Personally.
16 meters.
What?
Is the highest. Obviously, that doesn't all occur, at once, and that's from highest to lowest as well. It's not from normal to peak. So that's water, right? So that's essentially the gravitational effect of the moon kind of pulling that water closer to it, right? So the Earth is not perfectly spherical, right, as a result. You want to know how much Io changes how much its surface moves? This is going to be pretty trippy. And don't forget, it's made out of like rock and stuff. It's 100 meters. Right, so that might not sound much, but that's a pretty, if you think about the effect of the moon on water, right, which has an awful lot less structure, these orbital perturbations basically mean that Io is basically getting squeezed down, so its equator bulges out by 100 meters every, I think it must be at least twice every orbit. And so essentially the Io is just doing this, kind of just constantly being squeezed in and out. And that squeezing, that flexing, that's what leads to all of the heat in Io, and actually all of the heat in that system, right? And so that has pretty major consequences, because essentially what I want to show you now is a comparison, right? So we've talked a lot about how the further away from the sun you are, the less heat you have, right? Well, in the Galilean system, the further away you are from Jupiter, essentially the less the effect of gravity of Jupiter is on you, right? Because you're further away, but also the more complex the effect of the other moons, Galilean moons, in terms of your orbit. So Io, which is the closest in, is actually the most volcanic place in our solar system. It has hundreds and hundreds and hundreds of volcanoes constantly erupting on its surface. And if you look at its surface, it's really smooth, right? These black dots are volcanoes, basically, right? And if you look at it really, really, really close up, which is what the bottom panel is, it looks like it's smooth as a liquid, right? It's not. It's solid. There's no liquids on its surface, but it's super, super smooth. If you look at Callisto on the other extreme, right, which is not subject to this orbital resonance, and it isn't tidally heated really at all, it has so many craters on its surface that I actually think if a meteoroid hits it, it will erase more craters than it creates. That's how cratered it is. It's like craters on craters on craters, right? It is the most cratered object in the solar system, right? And the reason for that is that Io is being heated an extraordinary amount. Callisto is not. So Io constantly resurfaces its surface, right? It's not that Io and Callisto get hit by fewer pieces of space junk. It's that Io constantly covers its surface, whereas Callisto does not. And so all of the impacts, their record stays there essentially. And then we've got the in between those two extremes with Europa and Ganymede. So you can see this in their surfaces. Europa, we're pretty sure, is has a salty ocean under its surface, which is why everyone's so interested in it as a site for life. And essentially, these lineae. That's another good word of the day. We already had that one. These lineae are cracks in the ice, essentially. And if you zoom in even further, you can see that over there. And they actually, I'm kind of looking even closer myself, they crisscross over each other, right? So there's an awful lot of ice flexing, cracking, coming back, being, resurfaced, things like that. There's a fair amount of activity there. And if you look at Ganymede, it's essentially something kind of in between Europa and Callisto, right? It has craters on its surface, which Europa largely doesn't, but it does still have these cracks. So we do think that Ganymede has an icy core, icy crust, sorry, and potentially an ocean underneath it, but it's much less hot than Europa is. So essentially, where those moons are in this system and in this case of tidal heating has a massive effect on what its properties are, right? And therefore its suitability potentially for life. Now I'm going to just pause there for a second before we get on to Io, because I want to have, if anybody has any questions about tidal heating. It's not the first time we've come across it, but it is a pretty important concept to get. If you got any questions, just fire away and ask.
Do you have the chat open?
Let's see. Nope, not that one. Oh, here we go. Oh, I'm sorry. Oh, shit bits. It's whenever I see I'm going through the PowerPoint, I can't see the chat for some reason. It's minimized. Where are we at? Come on, stop that. It's not the smoothest thing. Oh, diameter of the sun is about 900,000 miles. Oh, she's called Karen. That's a cute name for a cat. Yeah, so Robertson, the diameter of the sun is about 865,000 miles, something like that. And the distance of Earth to the sun is 92 million miles. So it's about 1 to 100 ratio. Dulcet. I didn't call him Dulcet. I said his voice was dulcet, which means sweet. That's for Vivian. Doesn't everybody think Paul has a sweet voice?
Stop, you're too much.
So sweet.
Very sweet.
It's Kiara, what does its GIF 16 meters mean?
Wait,
It's from
So-
earlier when you were asking about that animation. I was like, oh, I love a good GIF. Kiara was like, no, it's pronounced GIF.
Oh,
So, yeah.
16 meters was when you asked about the how much the planet is changed.
The
I mean,
tidal range.
oh,
Yeah.
and you got it. Good job. I'm sorry, I didn't
Crushed it.
catch that.
the
To Vivian, gravitational pull changes. No, because essentially it's trying to think of a good way to explain this. You know, I mean, if you think about it in terms of us, it's, you know, when the moon kind of goes overhead, it's not like we weigh less, right? It's something, these gravitational changes or effects only happen at really large scales, because at smaller scales like us or life, you really don't notice it. Essentially, that's because the difference in mass between the Earth and us is so huge that any change in the gravitational pull on us that the moon causes would be insignificant. It'd be too small to detect. But when you have something really large like an ocean, then you can observe a really large, you can actually observe the effect of this gravitational change. Other things related to Jupiter do have a big effect, and we'll get into that when we go into Io. So good question though. Let's scroll down. Cool. Awesome. Yeah, so thanks, Kiara. Give me a shout because I can't see the chat very easily when I'm going through the PowerPoint. So if there are questions that pop up, you know, just shout out and I'll check them so we don't get too far ahead of the questions. Okay, so let's go to Io. Look at that. Isn't that a disgusting looking moon?
It looks terrible.
It looks putrid, actually.
Yeah,
That's a pretty good word. Looks like something it looks like something my cat chucked up last night. I nearly stepped in this morning. Anyway, you probably didn't want to know that. We've got a very weird cat. So this is literally what Io looks like, right? All of these dots, you can see these black dots, are volcanoes. And they're called cryovolcanoes because it's not so much that things are really, really cold, although obviously Io is colder than the Earth. It's more that people don't want you to confuse them with the stereotype of volcanoes on Earth of just being these big eruptions of molten lava and stuff. However, you can see, and this is really neat, and we'll look at some pictures later that show in detail. Say this one in the center, right, this volcano here. You can actually see the ejector ring around it. So normally when volcanoes erupt, they kick material up into the atmosphere, which Europa kind of has, Io kind of has, sorry. And then it falls back down a little distance from the volcano. And so you can actually see that really neatly around a lot of these volcanoes. You have this kind of ring of ejector around them. which changes over time as well. And the reason why we think Io is yellow, we don't actually know for sure, is most of this is, we think, sulfur. So those volcanoes are spewing out most likely sulfur dioxide and other sulfur containing compounds. And those then settle back down onto the surface and give it that color. They also think that potentially these volcanoes erupt silicates. So essentially, it's like a quartz volcano, if you can think of that, or mica volcano, which is a little bit weird to think about because we don't have anything analogous here. But those, it's either silicates or sulfur compounds which are getting erupted out. And you can actually look at that if you get, look at this. Isn't that an awesome picture? So this is a edge-on picture of one of those volcanoes. You can see it right at the top. It's erupting, and they can go up several hundred miles, right? They eject way out, up out into space, literally. And then you can see the material kind of falling back down in like this kind of shower, like it's almost like a fire hydrant that's been knocked over right on the street. So, and Io has those all over its surface. That's why the surface of Io, which you can see in this image here, right, there are some kind of features over here and over here on the right of the image, but if you just look at that part in the middle, it's all smooth. It looks like it's liquid water, right? You know, be a, you know, some kind of balmy place in the Caribbean, let's say. But it's not, it's solid, right? It's just very freshly produced material that hasn't had anything smack into it yet. This is a neat image of Io, right? So it is large enough to have differentiated, right? So it had enough accretional energy to basically be molten and have the heavier, stuff, which is these iron and iron sulfides kind of condensed down into the center. I'm not entirely sure what ultramafic means. I didn't know what the word mafic meant at one point, but I've forgotten. No, I can't remember off the top of my head. Something to do with rocks, obviously. And then you have this thinnish crust. And if you look at that crust, this is essentially what it's looking like, right? So this is the crust about here. It's about 20 miles deep, give or take. And then you've got that mantle underneath, which is molten, right? Because of the constant squeezing and relaxing of the effect of Jupiter's gravity. And essentially you have this kind of convection deal within the crust where material is getting pumped up to the surface, and then material's cooling down and it kind of rotates like so. So this isn't named after the Brazilian footballer as far as I'm aware, but it's called Pelion Penteras. And so these are the kind of volcanoes, and you can see the ejector, right, landing at a distance from that. So astonishingly volcanic, right? There's an enormous amount of volcanic activity on Io. Oh, also, promised Vivian, I'll talk about this a little bit. Let's go back to here. So Jupiter, being that it's so massive, and also because it has essentially an enormous amount of charged particles in its upper atmosphere, right? So its atmosphere is thousands of miles thick, right? Varying in density and composition. But up near the top, you have an awful lot of charged ions, and those rotating around create a lot of electrical noise. And you also have a very massive core of something, we don't know what, rotating. And so Jupiter has a very powerful magnetic field. It's called a magnetosphere, right? And hang on, give me just a second. Work on the back of my bike on Friday, so might as well use it. Okay, I'm going to just stop sharing so I can see what it is I'm drawing. Here we go. Pardon me. Ta-da! Live action education. How about this? It's almost like I'm standing here in front of you. Anyway, actually, I might actually turn these lights off. There you go, so we don't have the reflection. Guess what that is?
Art. No, the big red spot.
Yeah, awesome. I know, terrible joke, right? Anyway,
Crushed it.
so here's Io, not to scale, right? But essentially you have these enormous magnetic field lines going like so, right? Obviously you can't see them because it's, there you go, that's better. Because they're not visible, but they look like something like that. And Io is orbiting through those. It's so close to Jupiter that it actually orbits within its magnetosphere. And as a result, there's a constant flow of electricity. This is about 3 million amps. That's not milliamps, that's million amps of electricity that flows from Io to Jupiter. It's like a giant electrical generator, basically. And also, and about, I think it's about 1 ton of material. So all of that, I don't know if you can read that, hopefully you can. A lot of that ejector, right, the stuff that's getting pumped up out of Io doesn't form an atmosphere because it's stripped off of Io by Jupiter as it rotates through that magnetosphere, and it kind of rides, essentially it's in the form of ions, right? So it's like a flow of charged ions from Io to Jupiter. And even cooler, sound effects, that causes lightning in Jupiter's upper atmosphere. How crazy is that? Oh, I think it's crazy anyway.
But like, wouldn't all this be terrible for life? Or do we know, like,
yeah,
living within something like this?
It would be pretty awful. But, and that's actually, I was thinking about this, but not impossible, right? So our next lecture, I was gonna go straight on to Europa and Ganymede, but I actually want to look at radiation resistance, because there is some life on Earth which is astonishingly resistant to radiation, right? So even though this sounds incredibly inhospitable, right, in terms of you know, the radiation from Jupiter, basically, right, it's not impossible. So yeah, I mean, to us it sounds awful, but we're not all life, right? So yeah, anyway, well, that was pretty cool. Let's stick that back down there. That live interactive online teaching. I'm like a poster child for online experiences or something. Anyway, So, what was this one about? Yeah, I mean, we kind of covered that quite well already. So just some more pictures, essentially, right? Because they're pretty. One of my favorite ones is this one to the bottom right. Trying to remember if that was from. Yeah, that must have been a Galilean picture that close, right? You can see, again, these are just more volcano pictures, right? So the center top picture, that blue thing just above my cursor, that's another volcano ejecting material into space. And here you can see even better in the bottom right picture. Isn't that just stunning? You know, you can see the terminator here, you know, between sun and dark, or day and night, I guess, on Io. And you can see this enormous volcano spewing stuff out. Imagine if that was analogous to Earth, right? That ejector would be what, 40, 50, 100 miles high, right? It would be like the volcano to end all volcanoes. Maybe if Yellowstone erupted, it would look something like that. I just watched 2012 on Netflix the other night. Anyway,
the movie is weird.
It's awesome. Totally
weird.
Totally improbable. I mean, how many times can you make like an amazing plane takeoff and not die? You know, and they made every single one of them, and landings too. Apart from poor Sasha, who got it on the nose. Anyway, that doesn't matter. So, but here's a really cool thing. So you can actually see this is the same volcano over time, right? So you can see how the ejector ring grows and shrinks. And here's another volcano which was quiescent here and then has obviously been erupting in between taking of this picture and this picture. Right, so you can see really cool stuff. Here are on the top right are some lava flows. So of what I don't know, we don't know, not just me, but humanity in general. But you can see these kind of lava flows spreading out down this volcano, which is pretty awesome. And here's just some more pictures, because these are cool. I don't know, I grew up watching the videos of Voyager and stuff like that. And so seeing things like this is just super awesome to me. And so this is, I think, a really beautiful picture of Io with Jupiter in the background. You know, I mean, Io is a fairly ugly looking moon, but that's a really pretty picture. So in terms of kind of going back to Paul's question too, a lot of, when we think about astrobiology, right, you have to think about life as you would on Earth, right? And so if you think about life on Earth, obviously there's a lot of big things like ungulates, right, which are on the surface of you know, part of the Earth, right? But really, if you think about life in terms of ecological niches, there are a huge number, right? There's more than one could count. And a lot of those are organisms that live in particular places which are protected from adverse conditions. So if you think about the Sonoran Desert, for example, right, in, is that Arizona, I think? You know, if you go out there in the middle of the day and you look around, you'll see nothing, right? If you wait until, well, maybe for longer, if you don't, you know, die from heat stroke, you'll actually see things start emerging from out underneath rock overhangs, for example. Or if you wait until it's a little cooler in the morning or the evening, you'll see those things start foraging and hunting and stuff like that. So when we think about potential of life elsewhere in the solar system, we can't think about it from an anthropocentric point of view, right? We can't think about, oh, you know, there's going to be stuff strolling around on the surface. We have to think about in terms of ecological niches. And so if we have volcanoes like this, right, and a heavily riddled crust because of all those volcanoes. If you just think about various islands in Hawaii, or even you know, I've gone through walked through lava tubes in, shoot, where was that? I think that was near Bend in Oregon, or a little bit further to the east. But anyway, oh no, Northern California. There you go. There's a whole load of lava tubes up there, and so that would most likely be an environment you would find on Io if things are analogous. And you know, there's a good reason to believe that they would be, right? If there's lots of volcanoes there, then they're most likely going to have similar features to volcanoes on Earth. And one of which of those is lava tubes. So where, you know, molten material flows underground and then stops flowing, for example. And so those would be potential ecological niches for life to emerge on Io. Still unlikely, right? You know, I mean, it is a hellish environment in terms of, particularly in terms of the radiation, but it's not impossible. Improbable, maybe, but not impossible. And also because if you think about some extreme environments on Earth, sulfur or reduced sulfur is one of the main electron donors for a lot of chemosynthetic bacteria. So there's a lot of that on Io. So yeah, I mean, it's possible. And what I'll do next, I'll get the PowerPoint finished and posted this afternoon, so you'll have time to go through that. We'll look at some examples of radiation resistance on Earth, and you'll be quite astounded. There's actually one called Conan the Bacterium, which is my favorite. We'll talk about that.
Wonderful.
Yeah. Who says scientists can't have a sense of humor, right? So yeah, anybody have any questions about any of that stuff? Let's just, I think we have, yeah, quiz coming up next Monday. So I better get off my ass and figure out how to do that. So that'll be something I'll be working on this week, along with the PowerPoints and stuff. And I'll let you know ahead of time what format that will take.
I have a conspiracy theory.
Oh, cool. I just love conspiracy theories.
I think that the moon is pulling water from Earth because it's really thirsty.
Well, you know what we were saying about, let's not think about it in an anthropocentric terms.
But like, you can't disprove it though, right?
Oh, well, I mean, actually, what's the name of the guy? Shoot, I can't remember his name. Something Teapot. So if I could actually look at my browser, let's see if I can get up a new one. It means using Internet Explorer, which was going to be a little bit unpleasant, but let's see if we can. Let's see. Come on. This is actually oh, there you go, Russell's teapot. Right, so no, you can't disprove it, but neither can you. So this is a really cool, it's actually a more theological argument, which I always be a little careful. But essentially, Russell's teapot states that, okay, actually, there you go, that's what it might look like. You know, if you have a teapot orbiting the sun between, I think it was between Earth and Venus, but it was too small to be observed, could you disprove that it's there? And the answer is no, you can't, right? So there may actually be a teapot orbiting the sun. Obviously, yep. There's questions about, well, how did the teapot get there? Right?
Isn't the burden of proof always on the person who's bringing the theory up, though?
Well, yes.
So, like, yeah. So if Kiara would need to prove that the moon is trying to steal the Earth's water and not just throw the idea out there.
Yes, that's one aspect. Actually, you should. I've spent some time reading up on Russell's teapot because there's some good arguments both for and against it. I don't really understand them well enough to try and summarize them, to be honest, because theology is not really my strong point, to be honest.
Okay, but like my point is, what if?
That's true. There's also lots of other things like, well, what if you're not actually a human, but you're a very, very effective robot and I can't tell the difference between something that is life and it isn't.
I feel like there's a good chance that I am both at the same time.
Right. So yeah, I mean, I think it's not the most testable of hypotheses, and I think if you wanted to build a career on it, you might struggle. But it's an interesting thought experiment.
Thank you.
Does anybody else have any? Thank you, Vivian. Yes. Well, to be honest, if it was Neil Armstrong, Vivian, probably it would be more of a coffee pot. We'd have to have had British people go up into space for them to leave teapots hanging around and stuff. Yes, that's right. Although I'm actually one of few British people that doesn't drink tea. I really don't like drinking tea at all. I was traumatized by my parents.
Don't you have like a whole proper set in your office though?
Yeah, but I don't have a teapot in my office though. I have a tea set, which is the sugar container and stuff.
I feel so betrayed.
Aesthetics.
Yeah, for aesthetics, exactly. Yeah, I don't drink tea at all. I haven't drunk a cup of tea for actually pretty much since I left home when I was 18. Because I used to have to drink tea whether I liked it or not, about like 5 or 6 cups a day. And
so you haven't had one in like 5 years?
No, I left. Well, I'm not that young. No, I haven't. Yeah, probably since, what would that be? 1996? No, 1999 maybe. Definitely since I left the UK. Like what was that? Like 14 years ago or so. I haven't had a cup of tea. And that's largely because I haven't been in my parents when my mum's always like, "You want a cup of tea?" "No, thanks." And then you get a cup of tea. It's like, I don't want a cup of tea. Anyway, even my dog used to get a cup of tea every evening. My dog. That's how much tea we drank. Anyway, that's not a particularly useful.
Wait, one more question. What do you think of how us Southerners use so much sugar in our tea?
Well, I'm not much of one for iced tea, so I don't really have an opinion on that. But I have a lot of sugar in my coffee. I usually have at least three spoons of sugar in my coffee. So yeah, I've got no negative opinion about overly sweet drinks, because that would be rather hypocritical of me. There you go.
Thank you.
Pronouncement. All right, everybody. Anybody got any other questions other than about hot beverages? No? Awesome. All right, so I'll post up the PowerPoint and audio for the radiation resistance topic, just because it'll be fun to talk about. It's pretty nuts when you think about how these things can survive. And then we'll finish up the Jovian system on Friday with Europa, and maybe if I can find enough interesting stuff, we'll talk a little bit about Ganymede too. All right. Thank you very much, everybody. See you on Wednesday.
Have a good day.
You too.
Thank you.